Welcome to Graph That, Episode 3, GenAI and Knowledge Graphs. If you aren't familiar with the Graph That series, we take public data sets and convert them to a graph model optimized for Amazon Neptune. Amazon Neptune is a fast, reliable, fully managed database service that makes it easy to build and run applications that rely on highly connected data sets. The core of Neptune is a high-performance, purpose-built graph database engine. This engine is optimized for storing billions of relationships and querying the graph with millisecond latency. Customers frequently ask for assistance on modeling their data for graphs, so we hope this series will inspire on the subject. In this episode, I'm going to cheat a bit and brush the dust off an old data set from a blog post. In that post, I took press releases from Amazon.com, ran them through Amazon Comprehend Events to extract entities and events from the unstructured data, and then modeled it into a graph. Today, we're going to reuse that data set as the foundation of our knowledge graph, and then we're going to utilize an LLM to query it. The original blog and source code to create the knowledge graph can be found using this URL or QR code. I know that a lot of information exists about retrieval augmented generation, or RAG, the variant called GraphRag, and GenAI in general. Many of these toolkits abstract the basics away and focus on just raw, unstructured information. But what if we already have structured knowledge? So before we dive in to our knowledge graph, first I'm going to cover the essentials about RAG, and then I'm going to show why GraphRag is an improvement over RAG. Then we'll do a quick recap of our existing knowledge graph model from the blog post. And finally, I'll show you how we can connect it up to an LLM easily just using the AWS SDK and some prompt engineering. No external toolkit required. So with that, let's get started. So first, how does retrieval augmented generation, or RAG, work? RAG is a machine learning technique that combines the strengths of language models and retrieval systems to generate more informative and accurate outputs. The key idea behind RAG is to use a retrieval module to find relevant information from a knowledge base or corpus, and then use that information to guide the language model during the generation process. The main advantage of RAG is that it can generate more accurate outputs compared to traditional language models, which may struggle with factual inconsistencies or lack of relevant information, commonly known as hallucinations. By leveraging the retrieval component, RAG can dynamically access and integrate external knowledge as needed, leading to more informed and contextually relevant responses. So how does all of this work? RAG generally involves taking unstructured documents, splitting them up into chunks, and then creating vector embeddings on each chunk. Vector embeddings are a way of representing words, phrases, or other data as numerical vectors, where each element in the vector corresponds to a particular feature or dimension. The key idea is to capture the semantic relationships and meaning of the input in a compact mathematical representation. Then we calculate vectors on the questions we are asking and search for those chunks that are most similar and share them with the LLM for use in generating the model. Let's see this in action. So first, here we are taking two press releases from our corpus. The first describes Amazon and Whole Foods markets and their merger back in 2017. And the second one is the text from a press release that talks about Amazon selling partner conferences selling out in 6 weeks. So as you can see, it doesn't have anything really to do with Whole Foods. So I'm going to add this text into my Neptune notebook here. And I'm going to install some tools, some Python tools that's going to help me analyze these. So I have semchunk, ticktoken, and scikit-learn. So first thing that needs to happen is, what is tokenizing? So what does tokenizing mean? Tokenizing is a way of taking a sequence of characters and it maps them to a set of numbers. And those numbers are going to be fed into the large learning model. So in this case, I'm using the CL100K base, which is one of the tokenizing models. Each LM model uses its own tokenizer, so I'm just using this as an example. And I took the first few words from that first press release. And so you can see that this generates 26 tokens. Each one of them is assigned a number. So the word Amazon becomes token 26,948. Open parentheses is 00320. And you can see if the token appears more than once, right? A space and then an open parentheses, that is assigned the same number. And so the way that these token models are generated is that they represent either a word or a part of a word that has meaning. So after we generate all these tokens, now what we do is we break up that document into a number of chunks based on a chunk size that's best for our model. For here, I just arbitrarily chose 128 tokens. So I'm going to run that same chunker over those two press releases. And you can see that the first document had, there's 13 chunks total. The first document makes up these first 3 chunks, and then that second document is the other 10. So now we have 13 chunks from those 2 documents. And now what we're going to do is we are going to generate the vectors on each one of these chunks. So here we have, we're going to use the Boto 3 library. It's called Bedrock Runtime. And we're going to use the model Titan Embed Text V2. So this is going to generate a sequence of numbers, of vectors, for each one of our chunks. So I run this, and it's going to take a second to make the calls out to Bedrock. And we could see that. So for instance, the first chunk we had, that ended up being 129 tokens. The size of the embedding was 1024, which is the output of the model. And you could see, so these are a bunch of numbers that represent essentially the semantic meaning of that chunk of text in a way that can be understood by the machine model. And then we continue this for each one of these block chunks. And then we're going to do the same process with the question we want to ask the LLM model. So in this case, our question is, what are the connections between Amazon and Whole Foods? So we go and we tokenize, we create the vectors for that as well. So you can see that the connections between Amazon and Whole Foods, the number of input tokens is 11 from this question. And it generates 1024 embeddings. And then we're going to calculate cosine similarity. So what we do here is we take each one of these documents, each one of these chunks of documents, and we calculate how far they are in terms of the 1024 vectors from the document, or from our question. So first, let's take a little bit closer look at exactly what cosine similarity is. Here we just have 2 sample documents that are completely fabricated and a question. So remember, in the case we had 1024 dimensions in our vectors. To make this simple, I just have 2. Right? So our question, the vectors are 0 and -1. And then we have 2 documents, one that's 2 document chunks, one that's -2 and 3, and one that's 2 and 1. So what we want to do first is we want to calculate the distance between each of these points. And so for just 2 dimensions, it's just the difference of the x1 and x2, multiply them by each other, and same thing with y1 and y2. So -2 times 0 is 0, 3 times -1 is -3. And then we add them together. So x plus y is -3. The -3 is the distance in this case. And down here, we can see the distance. The distance is -1. So now we've calculated distance. What we want to do is we want to calculate the magnitude. So the magnitude is, and there's libraries to do all this for you, so you don't really need to memorize this math. But essentially what it comes down to is we want to take the x and y, square each one of them, add them together, and then calculate the square root. So the magnitude on the first document is 3.61. Magnitude on the second document is 2.24, and the magnitude on our original question is 1.0. And so now we can calculate, now that we have the distance and the magnitude, we can calculate the cosine similarity by taking the distance and dividing that by the magnitude of the document, basically the magnitude of the 2 points, the distance between 2 points, and divide that by the factor of the two magnitudes multiplied by each other. So we can see the cosine similarity between the first document and our question is minus 0.832. And for the second document, it is minus 0.447. So you can see that the smaller value is to the right, and if you look at the distance of those of the lines, you can see that the second document is actually closer to our original question than the first one. So what we would say is that the second document is more similar, and the first document is less similar. So I run this, and I'm telling it to return the top three most similar documents. And so you can see the first document is, what we saw was our first chunk, which obviously had a lot to do with Whole Foods Market. So did the second one. And then the third closest document actually had nothing to do with it. It talks about the Selling Partner Summit. And so I'm just going to print out these three chunks so we can see. And you can see the first one, right? It's clearly talking about the Whole Foods Market acquisition. That's very relevant to our question. The second one talks more about details about Whole Foods. John Mackey is the co-founder and CEO, what they will continue to do under Amazon and so forth. And the third chunk is just kind of the summary of the press release about the Selling Partner Summit series, talking about different guide principles of Amazon and products, but it doesn't actually talk about Whole Foods at all here. So you can see the main issue here is that we were not able to, we arbitrarily chose top three, but we don't really know if all three of them are actually relevant. So if we take these three chunks of documents and pass it into the LLM, it may hallucinate. It may bring things up talking about partners or something like that isn't really relevant to the question. Where you might especially see this is if you're covering areas where you have two separate, the context is missing. Like let's say one document is talking about healthcare records and the other document is talking about like financial markets. There might be information in both of those that is, and if you care about healthcare markets, that financial market information probably isn't relevant to you, but things might get injected into the answer because of it. So we're going to pause there, and we're going to then move on to GraphRag. Okay, well, what is GraphRag then? So GraphRag extends the RAG that we just spoke about by also incorporating a graph element. Generally, the data will also be organized with nodes representing key entities from the chunk of information, and relationships between those key entities will be stored also. This allows us to retrieve information not directly referenced in the most similar documents, and also validate that those similar documents are referred to the key entities. So let's take a look at this. Here we have those same document chunks that we had before. And what we're going to do is we're going to define a prompt using the Cloud Haiku model. And what we're going to ask the LLM to do is identify entities from the text, from that chunk of document. And to keep this very similar to the original content from Comprehend Events, we are going to identify similar entities that were found in there. So I'm saying the entities that it can identify are organizations, dates, people, facilities, people titles, locations, monetary value, stock code, and quantity. And I also want to give it some more complex instructions. The way that Comprehend Events works is if it extracts a stock code, it formats it in a way that the market is in the market identifiers in front of it, a colon, and then the stock ticker code, because you can have the same stock ticker on multiple markets. So I'm telling you, if it's a stock code, I want it to do this where it's saying, for instance, the Citigroup is traded on the New York Stock Exchange, and this is how it would format the output. Apple is traded on the NASDAQ. It would format it like this. And if it doesn't know which market the symbol is traded on, it can just use unknown. And when somebody gives it text, I want it to identify these and return the output in this JSON format. So I'm going to take all 13 chunks of document that I have, and I'm going to run it through this model, or through this. I'm going to send it to the LM and have it identify these entities. So you can see here that we have some entities that's cut off on the string on this text, but it's okay. We'll see these more in detail later. But what it did is it went through all 13 chunks. This is a zero reference list, so it's 0 to 12, and identified the sets of entities from those documents. And now we're going to ask it to do the same thing for our question, right? So the instructions prompt here is, you're excellent at identifying entities from a question. It makes you happy and provide the correct answer. Pretty much the same instructions, and again, to return the JSON. So I'm going to ask it the question, what are the connections between Amazon and Whole Foods Markets Incorporated? And it's going to look at that question, and it's going to say, okay, I found two entities in that question, Amazon and Whole Foods Market Incorporated. And so to give you an example of just a subset of those entities that were extracted, we have document 1, document 2, here's the chunks that we're taking from each document, and here's the entities that are referenced. So you can see like Jeff Bezos, Whole Foods Market is in chunk 0 in Amazon. Chunk 1 identified Whole Foods Market Incorporated and John Mackey. Chunk 2 has 2017 in Amazon. And you can see some examples from the second document as well. It's not that's not a fully inclusive list. It's just some examples to give you an idea. And so what I'm going to do now is, now that I have all the chunks and the entities extracted from each of these chunks, including my question, I'm just going to create two simple pandas functions here that's going to pull out of the list if there's any entities that reference the certain word. So here I'm going to look for Amazon or Whole Foods Market Incorporated or Whole Foods, and I'm going to create new columns. Has Amazon, has Whole Foods Market, and I want to kind of show the results here. Right. So these are all sorted in order of that similarity that we calculated before. So remember that when we did just RAG, we essentially have this set of information, the first three columns. By adding in graph RAG, now we have these extra columns here, right? And so we can see that almost all of these documents reference Amazon, which you'd probably expect given their Amazon press releases. Only the first two documents reference Whole Foods Market. And notice that the second chunk there doesn't actually talk about Amazon at all. If you go back and look at it again, that chunk kind of was mostly talking about John Mackey and Whole Foods Market and what Whole Foods Market was going to be under Amazon, but it never actually spoke about Amazon. So graph RAG here we can see kind of takes that original RAG concept, right, which would have found this third document and said, well, that doesn't really, it would have included it if we said, show me the N, the K equals 3 nearest documents. But now we can actually add into our search and say like, well, wait, this doesn't actually talk about Whole Foods at all. So maybe I don't want to include that. And this one does talk about Whole Foods, but it doesn't talk about Amazon. But you can see that the RAG part of this was able to identify the context and say, well, this really is very similar to the question. As much as anything because it mentions Whole Foods Market directly, and so we probably want to include this. So this is why graph RAG gives you better results, right? Because in this case, it would omit this information that isn't really related to Whole Foods at all. Even though it's the third closest document, the fact of the matter is all these documents are not very similar, are not very relevant to our query. So great. Where are we going to go from this? right? And this is what I'm going to demonstrate today is that what if you already have all your documents in a knowledge base like this, right? And you don't have these vectors, you don't have this, but you want to make do with what you have. It is expensive to go and take all this text out and reorganize my entire knowledge graph. And so that is going to be our next section where we're going to talk about, right, what if I don't want to use RAG right now? Maybe RAG is down the road. How can I still take advantage of my knowledge graph using an LLM? So we'll be back in a second to talk about that topic. Before we get into the code, I want to give a quick overview of what the model from my existing knowledge graph looks like. So again, this is all detailed in the blog post that I shared at the beginning. But just to give it a quick update, our graph is formatted as a series of documents. Documents have one or more events, and events have one or more entities. In this case, the document references the full document. Remember, we're using our existing knowledge graph here, not the RAG process that we described in the graph RAG process we described. So a document in this case is a full press release. Inside that press release, Amazon Comprehend Events identified one or more events, and each one of those events has a number of entities that are associated with that event, and each with a role. So it goes document. Document has an edge called event that leads to the event. The name of the event is actually the proper name itself. So for example, is like acquires or corporate acquisition. And then there's entities in the role. So for example, acquiree might be Amazon, and acquiree would be Whole Foods Market, and acquirer would be Amazon. So now we just described the model. So now what do we want? Let's demonstrate how we can interact with that existing knowledge graph. So I want to use an LLM. I want this to be a natural language interface, a chatbot interface. And so first what I need to do is I need to set up how I'm going to interact with this. So I'm going to set up Bedrock to speak to our desired LLM. In this case, we're going to use Claude Haiku. And I have a series of questions here. I'll just go through the first one. And my question is going to be, what are the connections between the ticker AMZN and John Mackey? And much like we did before, I'm going to prompt the LLM to extract the entities that are coming out that I'm asking about. And I'm going to take this one step further from before, and then I'm also going to have the LM identify what type of question this was. There's two types that I'm supporting. One is an inquiry question. So this is something like, tell me everything about the entity, or a connections question, which is show me the similarities or the connections between entity 1 and entity 2. As you can see here, that and then I want it to output it in the JSON format like I did before. So I'm going to run this, and we will see that the LM identified that it's a connections type question, and the entities are the stock code, which is NASDAQ:AMZN, and the person, John Mackey. And no, I did not tell it anywhere. There's nowhere in my knowledge graph that says the stock code for Amazon is NASDAQ, right? The prompt said the stock AMZN, and in my prompts, I gave it examples for New York Stock Exchange and NASDAQ, but for the Apple stock, it just, it knew from its training that Amazon was part of NASDAQ, and therefore it inserted that in front of it for us. So now that we've identified, extracted those entities, we need to query our knowledge graph. So again, I have, I could rely on a plugin like LangChain to try to automatically generate the graph that, the query that I want given the schema of my graph. But I already know how to interact with my knowledge graph. So what I'm going to do is I'm going to just template the queries that I know needs to run. I'm very familiar with the structure of my graph. Obviously, I've been using this for a while. And so I am going to generate queries. And what these queries are going to show is they're going to extract the connections. So the first one's going to extract basically everything that is within a couple hops. So remember, we have document to event. Event has a role and the entity that's fitting that role. So what we're doing is we're going backwards from the entity that was identified to the event and then finding the other entities that are associated with it. And then we're also going to find other events that those entities are. So we're essentially doing like a friend of a friend type query or a two-hop query, something you might commonly see in like recommendation engines. And if we do want to find the connections, then we're also going to substitute in this extra little parts that tell it to filter where the beginning and the end or the intermediate parts. Sorry, the intermediate parts are those entities that we want because we are looking for a specific path. So I've created these query templates, and now what I want to do is I want to have the Neptune data plane API. I'm going to run these templated queries on the Neptune data plane API. So what I'm going to do is I'm going to go through that list of entities that I extracted, and I have some checks here to make sure that it's sending the proper information. It's not it identified two entities in the case of a connections query, not more, not less. So there are some kind of guardrails here, and then what it's going to do though is it's going to go and it's going to actually extract the facts that I told it to and write the queries. So I run this, and you can see the query that was generated. So this is the query, and I'm telling it to get the first, get at most 20 facts and entities here. And you can see the parameters that we're passing as well. So if you look at this query, you can see how it's parameterized, like there, entity one text, entity one label. And down here, you can see that it's the entity text is NASDAQ Amazon, the entity label is stock code, and then John Mackey, who's a person. So now let's go and look at all the statements that were generated by this. And so you can see the event type was corporate merger involving NASDAQ Amazon and the role of participant, and Whole Foods Market and the role of participant. And the document that was extracted from is this document here. There's a corporate acquisition. There is, employment. Whole Foods Market was the employer of John Mackey, and Whole Foods Market, again, employer. And this was referenced in a couple different documents. So now what we're going to do is, because we want to show what references these were in, I'm going to load the raw data, and inside the raw data it has the URL of the actual document. So I'm going to create this little reference table for the LM that is going to get the actual URL of the press release that these are extracted from, so they can return references and show me where it found the information that it extracted. All right, so now let's finally pull this all together. We are going to ask the LM to answer the question concerning the facts that we extracted using the LM in the previous call. So our prompt here is giving very specific instructions. Again, we're praising it, telling the LM that it's excellent answering questions and it makes it happy to. We're giving it that list of facts and the references that we had shared with it before. And we're telling it we want it to create a narrative paragraph answering the question below. And after the narrative paragraph, we want to include the facts as a bulleted list, but omit all those XML tags. We just want to see the facts. And finally, we want to list the references that it used after that list of facts. And so again, we template it with the question, which was, show me the relationships between AMZN and John Mackey. So I'm going to run this guy, and you can see first it's going to output all the prompt that we have. So, the full prompt that ends up getting sent to the LM is your excellent answering questions like we saw. And then notice how it's substituted in all the facts and the references that we gave it. And it's telling it to create the narrative list. And so we can see the output now, right? So here is how it answered. The facts provided indicate that Amazon acquired Whole Foods, with Whole Foods Market and its CEO, John Mackey, be involved in the transaction. Specifically, facts show that Amazon and Whole Foods were participants in a corporate merger acquisition, that John Mackey was an employee of Whole Foods Market. These connections suggest that the acquisition of Whole Foods Market by Amazon had a direct impact on John Mackey's employment status. And we can see the facts that were used that extracted. Remember, these are facts that were directly from our knowledge graph, right? And then also the references that those facts were from. So we reviewed how LMs and databases interact for RAG and graph RAG use cases. And then we explored how you can use LMs with your already constructed knowledge graph without having to start over, even if you don't have vector embeddings. You don't even need to use a popular RAG or graph RAG toolkit. Just the AWS SDK will do. If you have an open data set in mind you'd like to see transformed to a graph model, or a use case you'd like to see prototyped, please let us know in the comments of this video or reach out to me on LinkedIn at this URL or QR code. So again, this is Brian O'Keefe, AWS Neptune Specialist Solutions Architect, and thank you for watching. Keep on the lookout for our next episode of Graph That.